Right now, the universe is keeping a secret inside your body. Every atom in your hands, every cell behind your eyes should not exist. The early cosmos made matter and its mirror twin in near-perfect balance, and balance means nothing survives. Yet here you are. The reason is a flaw so small it borders on disbelief. One extra particle of matter for every billion pairs. Deep beneath France and Switzerland, a machine at CERN just caught that flaw in the act, and the strangest part is that the scientists who found it still cannot explain it. If quiet science helps you sleep, follow and subscribe. Tell me where you are watching from and what time it is for you. There is a belief you carry without ever deciding to. You carry it the way you carry your own weight, quietly, without noticing, until something asks you to set it down. The belief is this: that existence is the natural state of things, that the world is here because the world is supposed to be here. That matter, the stuff of your bed, your skin, the glass of water beside you, is simply the default condition of reality, the way an empty page is the default before anyone writes on it. It feels obvious. It feels too obvious to question, and that is exactly why it is worth questioning tonight. Because the people who study the smallest pieces of reality, the physicists who have spent lifetimes taking the universe apart to see how it is assembled, do not share your comfort. They look at the same world you do, the same stars, the same hands, the same quiet room, and they see something that should not be possible. They see a universe full of things in a cosmos that, by its own rules, should contain almost nothing at all, not a little less than we have, nearly nothing, a thin haze of light and empty space and silence. No galaxies, no planets, no warm body, lying still in the dark, listening. Let me show you how they arrived at that strange conclusion. Slowly, the way they did, so the ground can tilt beneath you the way it tilted beneath them. Start with the simplest fact about matter. Everything you can touch is made of particles. The air, the water, the bones inside your hand, all of it reduces, when you look closely enough, to a small family of fundamental pieces. For a long time, that was the whole story. Tiny building blocks, assembled into atoms, assembled into molecules, assembled into you. A clean picture, a reassuring one. And then, almost a century ago, the picture cracked open, and what came through the crack was a kind of twin. A young physicist, working only with mathematics, with equations describing how the smallest particles should behave, found that the math kept insisting on something extra. For every particle it described, the equations described a second version. Same mass, exactly. Same behavior, almost. But opposite, in a deep and specific way, opposite in charge. Opposite in the subtle internal properties that physicists track. A mirror particle. At first, this seemed like a flaw in the math, a ghost in the equations, the kind of thing you quietly ignore, but the universe did not ignore it. When experiments went looking, the mirror particles were there, real, measurable, born in the laboratory, and, as we would learn, born in the sky. It is worth pausing on how strange it was, historically, for this twin to arrive through pure mathematics before anyone had ever seen it. The equations were not asked to produce a mirror world. They simply refused to make sense without one. When you solve certain problems, the math hands you two answers, a positive and a negative, the way the square root of a number can point in two directions at once. For a long time, scientists were in the habit of throwing the second answer away, treating it as a meaningless artifact, a shadow with no substance. But this time the second answer would not be dismissed. It described something with real properties, a particle as concrete as the first, only opposite. And so a young physicist made a daring wager that the shadow was not a flaw in the math, but a prediction about the world, that the universe really did contain these mirror particles, waiting to be found. Within a few short years, in the tracks left by cosmic rays striking the upper air, the first one appeared, exactly as the equations had foretold. The shadow had been real all along. Reality, it turned out, was built in matched pairs. We call them antimatter. The word sounds like science fiction, like something invented for a story, and that reputation does it a disservice, because antimatter is not exotic and it is not rare in principle. It is simply the other half of the ledger. For the electron, there is the anti-electron. For the proton, the antiproton. For nearly every particle that makes up your body, there exists a partner that is its exact opposite, waiting in the structure of reality, like a reflection waiting in a still pond. Now here is where the comfort begins to drain away. Because a mirror twin is not a harmless thing. When a particle meets its antiparticle, they do not coexist. They do not bounce apart or settle into orbit around each other. They annihilate. The two of them vanish completely, and in the place where they used to be there is a flash of pure energy. Light streaming outward, the entire mass of both particles converted into radiation in an instant. Nothing is left behind. No fragment, no residue, no scar, just energy and then stillness. Let yourself feel the violence of that, because the numbers are difficult to hold in the mind. The famous relationship between mass and energy tells us how much light a tiny amount of matter contains, and the answer is staggering. A single gram of matter, less than the weight of a paperclip, meeting a single gram of antimatter, would release energy comparable to a powerful nuclear weapon. Not metaphorically. Actually, the smallest pinch of matter holds, locked inside it, an ocean of energy, and annihilation is the key that opens the lock all at once. Two opposites touch, and a city of light blooms where they stood. So now imagine the universe at the very beginning. Not the calm, slow universe of tonight, but the universe in its first instant, impossibly hot, impossibly dense, a furnace with no walls. In that furnace, energy and matter trade places freely. Light becomes particles, particles become light, back and forth, the way water becomes steam, and steam becomes water near a boil. And here is the crucial part. When energy turns into matter, it does not cheat. It plays fair. It makes particles and antiparticles together, in pairs, one of each, always balanced. This is not a guess. It is one of the most carefully tested rules we have. Make matter from pure energy, and you make exactly as much antimatter alongside it. Sit with what that means for the early universe. If the cosmos began as a sea of energy, and if energy makes matter and antimatter in perfectly equal amounts, then the young universe should have contained exactly as much antimatter as matter, a perfect ledger. Every particle balanced by its opposite. And you already know what opposites do when they meet in a furnace that hot and that crowded. They find each other. They annihilate. They turn back into light. Follow that logic forward, and you arrive at a conclusion that sounds like the end of a story before the story has begun. A perfectly balanced universe should have erased itself. As it expanded and cooled, every particle of matter should have found a partner of antimatter, touched it, and vanished into radiation. The cosmos should have spent its entire material inheritance in the first fraction of a second, converting all of itself into a fading glow. What would remain afterward is light, spreading out forever through expanding space, growing dimmer and colder and more lonely with every passing eon. A universe of afterglow, a universe with no one in it. That is the universe the rules predict. A bright, empty, silent nothing. And yet, look at your hand, move your fingers, feel the slow rise of your own chest as you breathe. You are not nothing. The room around you is not nothing. The earth beneath the room, the sun that the earth circles, the 2 trillion or so galaxies scattered across the reachable cosmos, none of it is the thin afterglow the rules demand. The universe is not empty. It is furnished, crowded even, with structure piled on structure, atoms gathered into worlds, worlds gathered into systems, systems into galaxies, galaxies into vast luminous webs that stretch across distances no mind can truly picture. Somewhere between the prediction and the reality, something went wrong, or something went right. It depends entirely on whether you would prefer to exist. This is the puzzle physicists call the matter antimatter asymmetry, and I want you to notice how personal it is, even though it is dressed in the cold language of particles. It is not an abstract riddle about distant things. It is a question about why there is a you at all. The same logic that erases the early universe, erases the carbon in your cells, the iron in your blood, the calcium in your bones. Every atom you are made of is matter that, by the strict accounting of the early cosmos, should have met its antimatter twin and disappeared in a flash of light before the universe was a second old. You are made of survivors. You are made of the particles that, somehow, did not get erased. And the question that physicists cannot stop asking, the question that has pulled some of the finest minds of the last century into windowless laboratories and underground tunnels, is simple to say and brutal to answer. Why did anything survive? What broke the perfect balance? What allowed even a single particle of matter to outlast the great annihilation and become the seed of everything? Notice that the rules, as we wrote them, do not allow for this. That is the part that should unsettle you. It would be one thing if our best theory of reality predicted a small surplus of matter, an explanation built quietly into the equations. But that is not the situation. Our most successful description of the particle world, the framework that has passed every laboratory test we have thrown at it for 50 years, naturally produces a balanced universe, a self-erasing one. The survival of matter is not a prediction of the theory. It is a violation of its expectations. The fact that you exist is, in the strictest sense, a clue that the rules are incomplete. Let that reframe settle over you slowly. You were raised, without anyone saying it aloud, to think of your own existence as ordinary, as given, as the boring baseline from which interesting questions depart. But the deeper you look, the more your existence stops being the baseline and starts being the mystery. The empty universe is the expected result. You are the anomaly. The dark, silent, lifeless cosmos is what the math wants. The warm, crowded living one is the surprise that demands an explanation we do not yet fully have. There is a particular kind of vertigo in this, and it is not the vertigo of fear. It is closer to the feeling of standing at the edge of something enormous and realizing, for the first time, how far down it goes. You came here tonight expecting a story about a machine in Europe, about scientists and discoveries, and we will get there, I promise you. But before we can understand what happened at CERN, before we can understand why it left even the experts saying that they cannot fully explain it, you have to first feel the weight of the thing they are trying to explain. You have to let go of the comfortable belief that existence is free. It is not free. It was paid for, somehow, by a flaw in the balance. A flaw so small that we have spent 100 years trying to find where it hides. Let me sit with you a little longer in this strange new feeling, because it deserves more than a passing glance. For most of human history, the great question was why things end. Why the candle gutters, why the body fails, why the warm afternoon slides into evening and then into dark. Endings felt like the natural pull of the world, and existence felt like the thing that simply was, the canvas on which all the endings were painted. But the physics turns that intuition inside out. The physics says that ending, in the deepest sense, was the easy part. The universe knew exactly how to erase itself. It had the instructions written into its own balanced rules. What it did not obviously know how to do, what it should not have been able to do at all, was to keep anything. Persistence is the miracle. Existence is the thing that demands an explanation, and no one has fully given one. Consider how thoroughly this overturns the ordinary picture. You probably imagine, somewhere in the back of your mind, that the early universe was a kind of warehouse, stocked full of matter, and that over time some of it got arranged into stars and worlds and creatures. A picture of abundance, slowly organized. But that is not what the rules describe. The rules describe a warehouse that was built to empty itself completely, a warehouse whose every shelf came paired with a mechanism to cancel its own contents to nothing. The fact that anything is left on any shelf at all is the surprise. We are not the organized portion of an abundant beginning. We are the unexplained survivors of a beginning that was designed by its own logic to keep nothing whatsoever. And notice how the mirror twin makes this worse, not better. If antimatter did not exist, if particles had no opposites, then a universe full of matter would be unremarkable. Matter would simply persist because nothing was built to destroy it. But that is not the world we live in. We live in a world where every particle has a perfect adversary, where the very act of creation hands out destroyers along with the created, one for one, in lockstep. It is as if every brick that was ever made arrived bonded to a brick eater, a thing whose only purpose was to find that brick and reduce both of them to light. Build a house that way, brick and brick eater together, and you should end with an empty lot and a flash of heat. You should not end with a house. And yet here is the house, here is the room, Here is the body in the room. There is one more layer to feel before we move on, and it is the layer that makes this personal rather than merely cosmic. The annihilation we have been describing is not safely confined to some abstract early universe. The rule still holds today. If a particle of antimatter drifted into this room right now and touched the matter of your hand, it would not pass through harmlessly. It would annihilate, releasing its little burst of light, obeying the same law it obeyed in the first second of time. The only reason this almost never happens is that there is almost no antimatter left anywhere near you. The great annihilation was so thorough that the universe you inhabit is, for all practical purposes, swept clean of the opposite. You live in a world made entirely of survivors, precisely because the destroyers have already been spent. The peace of this quiet room is the peace that comes after a war so total that one entire side has vanished from the field. So here is the open loop I want you to carry with you, down into the dark and the quiet, as we go deeper. Matter and antimatter were made in equal measure. Equal measure means total annihilation. Total annihilation means an empty universe. And yet the universe is not empty. The universe is full and warm and aware of itself through your eyes right now in this room. Somewhere, in the first unimaginable instant of time, the ledger came out wrong, by a hair, by a whisper, by the smallest margin the cosmos has ever kept. In the next part, we are going to count that margin. We are going to put a number on the flaw that made you possible, and that number is going to be far stranger, far smaller, and far more beautiful than you are expecting. Because the universe did not survive by a comfortable surplus. It survived by almost nothing at all. It survived by a remainder so thin that the wonder is not that the cosmos is so empty. The wonder is that anything was left to fill it. And do not let anyone tell you this is a question only for specialists, a technical curiosity with no bearing on your life. It is the most personal question there is, dressed in the clothing of physics. Why is there something rather than nothing? Why did the universe keep anything at all? Why are you here to ask? These are the oldest questions human beings have ever posed, asked around fires long before there were telescopes or colliders. And what is remarkable about our moment in history is that we have finally built instruments precise enough to chase them into the laboratory. The wonder you feel lying here is the same wonder, in an unbroken line, that your distant ancestors felt, looking up at the same stars. We have simply learned to ask it more sharply. The answer is still out there in the dark, waiting. Stay with me. Breathe slowly. Let the room go soft at its edges. We are about to look at the single most important leftover in all of existence, the one without which there would be no stars to fall asleep beneath, and no one beneath them to fall asleep at all. Hold that thought loosely, the way you would hold a small warm stone in your palm, and let it lead you gently into the next part of the story, where the leftover finally gets its number, and the number turns out to be smaller and stranger and lovelier than you could have guessed. Let us go back to the beginning, as far back as the mind can travel, to a moment so early that the word moment barely applies. The universe is less than a single second old. There are no atoms yet, because atoms are far too fragile for this heat. There are no stars. No light in the sense you know it, only a roaring sea of energy and the particles that boil out of it and dissolve back into it. This is the furnace we spoke of, and now we are going to stand inside it, carefully, and watch the most important accounting in the history of existence take place. In this furnace, there is a kind of ledger, not a real book, of course, but a perfect bookkeeping that the laws of nature enforce without effort. On one side of the ledger, matter. On the other side, antimatter. And the rule of the furnace, the rule we met in the first part, is that these two columns must stay balanced. Every time energy condenses into a particle of matter, it must also create a particle of antimatter, one for one. No exceptions that the simple rules allow. The columns rise together as the universe fills with particles, and they fall together as those particles meet and annihilate and return to light. Up and down, creation and destruction, a vast breathing rhythm of existence appearing and vanishing billions upon billions of times in less time than it takes a thought to form. Now, I want to give you the number that this entire story turns on, the number that physicists chase across decades and continents. When you tally the ledger of the early universe, matter against antimatter, the two columns are not quite equal. They are almost equal. They are equal to a degree of precision that is difficult to even speak aloud, but not exactly. For roughly every billion particles of antimatter, there were about 1,000,000,001 particles of matter. One extra, 1 in a billion, unpartnered, with no opposite to meet, no twin to annihilate against. Hold that ratio in your mind, because it is easy to say and almost impossible to feel. 1 in a billion. Let me try to give it a shape you can hold. Imagine 1,000,000,000 grains of sand, not a handful. A volume of sand, large enough to fill a small building, every grain a particle of antimatter. Now beside it, the same enormous pile, but with a single extra grain on top. That one grain, alone, balanced on the summit of a mountain of its opposites, is the entire margin by which the universe chose existence over emptiness. Everything you have ever seen, every star you have ever wished upon, every face you have ever loved, is built from that one extra grain repeated across the whole cosmos. The other billion grains, matter and antimatter alike, did exactly what the rules demanded. They found each other. They touched. They vanished. Before we follow the ledger to its end, let me make sure the timing of all this lands, because the speed of it is part of the wonder. We are not talking about events that unfolded over centuries or even over years. The entire drama of creation and annihilation, the rising and falling of the columns, the great cancellation that spent the wealth of the cosmos, took place in a sliver of time so small that the word instant flatters it. By the time the universe was a single second old, the decisive accounting was essentially complete. The matter that would build every galaxy you will ever see had already been chosen, already separated from the antimatter that would destroy nearly all of it, already set on the long path toward becoming stars and worlds and bodies. Everything that has happened since, the entire 14 billion year history of the cosmos, the formation of galaxies, the lives and deaths of countless stars, the slow emergence of life on at least one small world, all of it is the working out of a decision the universe made in less time than it takes your heart to beat once. The leftover was determined in a flash. Everything after has been consequence. And so the great annihilation came. As the universe expanded and began ever so slightly to cool, the furnace could no longer keep remaking the particles it destroyed. The balance tipped from creation toward destruction, and the columns of the ledger began their final descent together. Matter found antimatter across the entire breadth of the young cosmos, and pair, by the countless trillions, they annihilated. The universe lit up with the radiation of its own self-erasure, a flash beyond any flash, the conversion of nearly all the matter that would ever be created back into pure light. This was not a gentle process, and it was not a small one. Picture the scale of it. For every single particle of matter that survives in the universe today, for every atom in every star and every world and every living body, roughly 1 billion particles of matter and 1 billion particles of antimatter were destroyed in those first instants. The cosmos spent almost its entire material wealth in one blinding transaction. What you think of as the full universe, all those galaxies, all that grandeur, is the tip left over after the cosmos paid away nearly everything it had. And here is something quietly astonishing. That light, the radiation from the great annihilation, did not disappear. It is still here. It surrounds you right now, in this room, passing through your body as you lie still. As the universe expanded over billions of years, that ancient light stretched and cooled along with it, sliding down from blinding radiation into a faint, cold whisper of microwaves that fills every direction of the sky. We call it the cosmic microwave background, and it is the oldest light there is, the afterglow of creation, the receipt for the great annihilation. When physicists point their instruments at the empty dark between the stars, they find it humming there, almost perfectly smooth, a sea of ancient warmth left over from the fire. And when they measure exactly how much of that light there is, and compare it to how much matter survived, they can read the ledger directly. They can count the ratio of leftover light to leftover matter, and that ratio tells them the size of the original imbalance. This is not speculation. This is measurement. Two completely different ways of weighing the early universe, the ancient light and the surviving matter, agree on the same astonishing figure, about 1 part in 1 billion. The flaw is real. The flaw is measured. The flaw is written across the entire sky in the faint glow of the oldest light in existence. So let us state plainly what survived. After the furnace cooled, after the great annihilation spent the wealth of the cosmos, what remained was the lonely remainder, the 1 in 1 billion, the unpartnered matter that had no antimatter left to destroy it, because its potential partners had already been used up balancing the rest. This thin residue of survivors drifted in the expanding dark, and over the slow ages that followed it began to gather. Gravity, patient and relentless, pulled the survivors together. Clouds of surviving matter collapsed into the first stars. Stars forged heavier elements in their cores and scattered them outward when they died. Those elements gathered into worlds. On at least one world, they gathered into something that could wonder where it came from. This is the part I do not want to rush, because it is the quiet heart of the whole story. Everything is built from leftovers, not from the main event, but from the remainder after the main event was over. You are not made of the universe the cosmos intended to keep. You are made of the fraction it failed to destroy. The carbon in the dark folds of your brain, the oxygen moving through your blood, the iron that lets that blood carry warmth to your fingertips, all of it is salvage. All of it is the one grain on the summit of the mountain, the survivor of a catastrophe so total that survival itself was a rounding error. There is a strange tenderness in that, if you let yourself feel it. We tend to think of ourselves as solid, as central, as the obvious occupants of a universe made for occupation. But the truth is gentler and stranger. We are the part that got left behind when nearly everything else departed into light. We are the residue of an almost perfect cancellation, and the almost is everything. If the cancellation had been perfect, if the ledger had balanced to the last particle, there would be no salvage to gather, no clouds to collapse, no stars, no worlds, no slow, warm rhythm of breath in a dark room. There would only be the light of the great annihilation, spreading out forever through an expanding emptiness, with nothing left to ever see it. So the asymmetry is not a minor footnote in the story of the universe. It is the reason there is a story at all. And this is exactly where the comfort runs out and the real mystery begins. The mystery that will carry us all the way to a machine beneath the border of two countries. Because I told you that the furnace plays fair. I told you that energy makes matter and antimatter in perfectly equal amounts, 1 for 1, and that this is one of the most carefully tested rules we have, and it is. So how, then, did the ledger come out unequal? If creation is balanced and annihilation is balanced, where did the extra grain come from? What put one more particle of matter on the summit of that mountain? This is the question that should keep you awake, except that I would rather it help you sleep. So let me frame it gently. Somewhere in the first fraction of a second, the universe must have done something that the simple rules forbid. It must have found a way, however briefly, to make a little more matter than antimatter. Not much. It did not need much. It needed 1 extra particle per billion, which is to say it needed the faintest possible thumb on the scale. But even that faint thumb is a profound problem, because our deepest understanding of how particles behave does not provide a thumb large enough. The rules, as written, can tip the scale a little. They are not perfectly balanced. But when you measure how much they can tip it, the answer falls catastrophically short. The cosmos needed 1 part in a billion. The known rules supply far, far less. That is the gap. That is the unexplained thing at the center of this entire video. The universe is full of matter. We can measure exactly how full. We can read the imbalance in the oldest light in the sky. And when we ask our best theory of reality to account for that imbalance, the theory shrugs and offers us a number hundreds of millions of times too small. The flaw that made you exists, we have weighed it. We simply cannot, with the laws we currently possess, explain how it got there. For decades, this has been one of the great open wounds in physics. A place where the theory and the universe disagree not by a little, but by an enormous margin. And the only way to close a gap like that is to go looking directly for the missing ingredient. To build machines that recreate, in miniature and for the briefest instant, the conditions of that ancient furnace. To smash particles together at nearly the speed of light, to make matter and antimatter fresh, and then to watch, with unimaginable care, for any sign that nature treats the two differently. To catch the universe, if we can, in the act of breaking its own balance. That is what they built beneath France and Switzerland. That is the machine you came here to learn about. And in the next part, we are going to descend into it, into the cold and the dark and the staggering precision of the largest scientific instrument humanity has ever made. And we are going to meet the principle it was designed to test. The principle that says matter and antimatter should be perfect mirror images of each other. And we are going to learn the name physicists give to the moments when that mirror cracks. Let me linger on the scale of this remainder, because the number 1 in a billion is so easy to say and so nearly impossible to truly hold. We use the word billion casually in the way we talk about money or distances, and it slides past the mind without leaving a mark. So let me try again to give it weight. If you wanted to count to a billion, out loud, one number every second, never sleeping, never pausing to eat or rest, it would take you more than 30 years. 30 years of unbroken counting just to reach the number that describes how many particles had to be destroyed for a single one to survive. Now imagine that you reach the end of those 30 years, exhausted, having counted away an entire human generation, and the universe hands you back exactly one particle. That single particle against your 30 years of counting is the margin. That is the abundance the cosmos kept. Everything else, every other number you counted, annihilated into light. And yet, and this is the part that turns the loss into wonder, that thin remainder was enough. Enough is doing extraordinary work in that sentence. A surplus of 1 in a billion does not sound like the foundation for a universe of 2 trillion galaxies. It sounds like a rounding error, like the kind of discrepancy an accountant would ignore. But the early universe was so unimaginably full, so densely packed with particles in its first moments, that even one survivor in a billion adds up, across the whole vastness of the cosmos, to every atom that has ever existed. The lake was filled, drop by improbable drop, by the tiny fraction that escaped the drain. The grandeur of the night sky, the sheer overwhelming quantity of stars, is what 1 in a billion looks like when the original total was beyond all counting. The remainder is small as a fraction and infinite as an experience. There is a particular image I want to leave with you here, because it captures the strangeness better than any number can. Picture the early universe as an ocean, and picture matter and antimatter as 2 tides, one rising as the other falls, almost perfectly opposed. For a perfect ocean, the tides would cancel and the surface would go flat and still forever, a mirror of nothing. But these tides did not quite cancel. By the faintest imaginable margin, one tide was a hair higher than the other. And when the great cancellation came, when the 2 tides crashed together and annihilated into light, what was left behind was not a flat and empty surface. It was the thin film of water that the higher tide had carried just beyond the reach of the lower. That film, that delicate skin of surviving matter left on the shore of the cosmos, is everything. It is the stars and the worlds and the oceans of the earth and the water in your own cells. We are the tide that did not quite go out. And remember, none of this should have happened. That is the thread we must not lose as we marvel at the remainder. The tides should have matched. The ledger should have balanced. The rules of creation, the fair exchange of energy into equal matter and antimatter, give us no reason for one tide to stand higher than the other. Something, in the first fraction of a second, leaned on the scale. Something made just a little more matter than antimatter against the grain of the very laws that govern creation. We have measured that something in the oldest light in the sky. We have weighed it precisely, and we still cannot say what it was. The remainder is real. The survival is real. Your body is the proof of it, and the cause remains a mystery that has resisted a century of the finest minds we have. For now, rest in the strangeness of what we have found. The universe was supposed to balance to nothing. It balanced, instead, to you. One extra grain in a billion, gathered across 10 billion years into a body lying quietly in the dark, wondering how it came to be here. The wondering itself is the leftover, thinking. And carry one more gentle thought into the dark with you. The leftover is not a sad thing, though the language of loss might make it sound that way. Yes, nearly everything annihilated. Yes, the cosmos spent almost all of its wealth in the first instant. But the thin remainder that survived was not impoverished by what it lost. It was liberated by it. Freed from the constant threat of meeting its opposite, the surviving matter was finally able to do something matter had never been able to do in the crowded furnace. It could endure, it could gather, it could build. The emptying of the universe was also the clearing of a space in which structure became possible, in which a particle could last long enough to find another and form something larger than itself. The great annihilation was not only an ending, it was the act that made beginnings possible. You are a beginning that the ending made room for. Let that settle, and we will go deeper still. If you wanted to catch the universe breaking its own balance, you could not simply wait for it to happen in the sky. The great annihilation finished its work in the first instant of time, billions of years before there were eyes to witness it. The furnace has long since gone cold. So if you want to study the flaw that made you, you cannot travel back to it. You have to rebuild it. You have to make, here and now, a small piece of that first second, again and again, and watch it more closely than anything has ever been watched. That is what sits beneath the green farmland on the border of France and Switzerland, near the old city of Geneva. From the surface you would never know it was there. There are quiet fields, a few unremarkable buildings, mountains in the distance holding their snow. But below your feet, in a tunnel buried deep enough to be shielded from the noise of the world, there runs a ring. The ring is enormous. It traces a circle roughly 27 kilometers around, large enough to encircle a city, carved through solid rock and kept colder than the deep of space. This is the Large Hadron Collider, the largest and most complex machine human beings have ever built, run by the laboratory we call CERN. The idea behind it is brutally simple, even though the engineering is almost beyond belief. Take particles, the tiny pieces of matter we have been talking about. Push them with powerful fields until they are moving at very nearly the speed of light, so fast that they loop around the entire 27-kilometer ring more than 10,000 times every second. Send two such streams around the ring in opposite directions, and then, at a few precise points, steer them into each other. When two particles moving that fast collide head-on, their energy of motion becomes, for the briefest flicker, a concentration of pure energy, and you already know what pure energy does. It condenses back into particles. Matter and antimatter born together, fresh, in a tiny recreation of the early furnace. For an instant, in the heart of the collision, the conditions resemble the universe when it was a fraction of a second old. New particles bloom out of the energy, exotic and short-lived, particles that have not existed naturally anywhere in the cosmos since the great annihilation ended. They appear, they fly outward, and almost immediately they fall apart, decaying into lighter, more familiar pieces. And it is in that falling apart, that decay, that the secret hides. Because if matter and antimatter are truly perfect mirror images, then a particle and its antimatter twin should fall apart in exactly the same way, at exactly the same rate, producing exactly the same debris. Any difference at all, is a crack in the mirror. So now we have to talk about the mirror itself, because this is the principle the whole machine was built to test, and once you understand it, everything that follows will land. Physicists have long believed in a set of deep symmetries woven into the laws of nature. A symmetry, in this sense, is a kind of fairness. It is a rule that says you can change something about a situation and the underlying physics will not notice. One such symmetry concerns charge, the property that makes matter and antimatter opposite. Swap every particle for its antiparticle, and the laws should behave the same. Another concerns the mirror itself, what physicists call parity, the question of whether the universe treats left and right the same way, whether a process and its mirror image obey the same rules. For a long time it was assumed that nature honored both of these fairnesses perfectly, that the universe was, at its deepest level, indifferent to the difference between matter and antimatter, and indifferent to the difference between left and right. And then, piece by piece, that assumption fell apart. The first crack came in the 1950s, when experiments revealed that nature does in fact care about left and right. Certain processes, it turned out, came out differently from their mirror images. The universe was not perfectly even-handed after all. This was a shock at the time, a genuine blow to the sense that reality was built on flawless symmetry. But physicists found a way to rescue the deeper fairness. Perhaps, they reasoned, nature only respects the symmetry when you do two things at once. Swap matter for antimatter, and flip left for right, both together, and maybe then the laws would look the same. This combined fairness, charge swapping plus mirror flipping, was given a name. They called it CP symmetry, two letters standing for the two changes performed together. And for a brief while, it seemed that this combined symmetry might be the true, unbreakable fairness at the heart of physics. That hope lasted less than a decade. In the year 1964, an experiment studying a particular kind of unstable particle, a particle called the kaon, found something that should not have been there. The kaons and their antimatter versions, when they decayed, did not behave as perfect mirror images, even with both changes applied together. There was a tiny difference, a faint preference, a hair of asymmetry between how matter and antimatter played out. It was small. It was almost lost in the noise. But it was real, and its meaning was enormous. The combined fairness, the CP symmetry that was supposed to be unbreakable, was broken. Nature, at some deep level, was not perfectly even-handed between matter and antimatter after all. The mirror had a flaw in it. It is hard to overstate how unsettling that discovery was to the people who made it. Symmetry had been a guiding faith in physics, almost an aesthetic principle, the belief that the deepest laws should be beautiful and balanced and indifferent to the labels we attach to things. A universe that genuinely preferred matter over antimatter, or one direction over its mirror, felt almost like a universe with a thumbprint on it, a sign that reality was not the perfectly even-handed machine it was supposed to be. Some of the physicists involved reportedly hoped, at first, that the result would dissolve under closer examination, that some overlooked error would restore the balance. It did not. The asymmetry held. Nature, it turned out, was not perfectly symmetric after all, and the people who loved symmetry most were the ones who had to let that belief go. There is a lesson in that worth carrying, that the universe is under no obligation to match our sense of what is elegant, and that some of the most important discoveries are the ones that force us to surrender a cherished assumption. We call that flaw, CP violation, and the moment it was discovered, it became the most promising lead in the entire mystery of why anything exists. Because here, at last, was a real, measured way in which the universe distinguishes matter from antimatter. If the early cosmos could treat the two even slightly differently, then perhaps that difference, multiplied across the entire furnace of creation, could leave behind a surplus of matter. Perhaps CP violation was the thumb on the scale. Perhaps this small flaw in the mirror was the very thing that allowed 1 grain in a billion to survive. For decades after that first discovery in the kaons, physicists hunted for CP violation wherever they could find it. They built bigger machines and more sensitive detectors. They found the flaw again in the 1960s result, then confirmed it more deeply in the years that followed. Around the turn of the century, they found it in a different and heavier family of particles, the B mesons, particles containing what physicists colorfully call the beauty quark. Dedicated experiments watched these beauty particles decay millions of times, and there it was again, the faint preference, the crack in the mirror, matter and antimatter parting ways by a hair. Each discovery was a triumph. Each one confirmed that the flaw was real and woven into the fabric of the laws. But each one also deepened a frustration that we will confront fully later, so I will only plant it here. Every time physicists measured CP violation in these particles, they could fit the result into the existing theory. The flaw was real, yes, but it was a flaw the theory already knew about, a small amount of asymmetry written into the rules. And when they added up all the CP violation the theory allowed, it was nowhere near enough to explain the surviving universe. The mirror was cracked, but not cracked enough. The thumb was on the scale, but the thumb was far too light. So the hunt continued, driven by a simple hope. Maybe there were other places to look. Maybe there were particles where the asymmetry had never been seen, where something new and larger might be hiding. And this brings us, at last, to the patient instrument at the center of tonight's story. Along the great ring of the collider, at the points where the particle beams are steered together, sit several enormous detectors, each one a cathedral of sensors built to watch the collisions and record what flies out. One of them is named LHCb, and it was designed for exactly one purpose above all others. It was built to study the beauty particles, the heavy, short-lived pieces of matter that carry the beauty quark, and to measure, with almost unbelievable precision, the tiny differences between how those particles and their antimatter twins fall apart. Picture what this detector has to do. In each collision, debris sprays outward in all directions, dozens of particles at once, most of them irrelevant to the question at hand. The beauty particles the physicists care about exist for a span of time so short it is hard to write down in words, a tiny fraction of a second, before they decay into other things. The detector cannot see the beauty particle directly. It can only catch the spray of lighter particles it leaves behind, reconstruct their paths, and work backward, like reading the splash to understand the stone. It must do this not once, but billions of times, sorting the rare and meaningful events out of an overwhelming flood of ordinary ones, building up, collision by collision, a count precise enough to reveal a difference of a few parts in 100 between matter and antimatter. This is precision on a scale that is hard to honor with words. To find an asymmetry of a few percent buried in billions of decays, you must control every source of error, every quirk of the detector, every way the machine itself might fool you into seeing a difference that is not really there. Whole careers are spent making sure that when the answer finally comes, it is the universe speaking and not the instrument. The patience this requires is almost spiritual. Thousands of physicists, across many countries and many years, all tending one enormous question, all asking the cosmos the same quiet thing again and again. Do you treat matter and antimatter the same? Or do you, somewhere, in some particle we have not yet checked, treat them differently? For a long time, every clear answer came from the same families of particles. The kaons, the mesons, particles made of a quark and an antiquark bound together. Important, beautiful, but not, in the end, the stuff that you are made of, because you are not made of mesons. The protons and neutrons in your atoms belong to a different and heavier category of matter, a category called baryons, particles built from 3 quarks bound together rather than 2. And across all the decades of hunting, across all the machines and all the discoveries, there was one glaring absence in the record. No one had ever caught CP violation, the crack in the mirror, the difference between matter and antimatter in a baryon, in the actual building block of ordinary matter, in the kind of particle that makes up your body and every solid thing you have ever touched. That absence was not for lack of trying. Baryons are harder, their decays are messier, the asymmetries expected to be subtle, the measurements brutally difficult. For years the result hovered just out of reach, hinted at but never confirmed, always falling short of the strict standard that physicists demand before they will use the word discovery. The crack had been seen in the mirror of mesons many times. In the mirror of baryons, the mirror that reflects you, it had never once been caught, until it was. Let me give you a fuller sense of just how extraordinary this machine is, because the numbers, like all the numbers in this story, are difficult to hold without help. The particles racing around that great ring are pushed to within a sliver of the speed of light, so close to that ultimate limit that the difference is almost beyond measuring. They circle the entire 27-kilometer loop more than 11,000 times in a single second. To keep them on that curving path, the machine uses powerful magnets, and to make those magnets strong enough, they must be cooled to a temperature colder than the empty space between the stars, colder than the faint afterglow of the great annihilation itself. So here is a quiet marvel worth pausing on. In order to study the birth of the universe, humanity built the coldest large region in the known cosmos, a ring of engineered winter buried beneath warm green fields. And inside that winter it kindled, billions of times a second, tiny sparks as hot as the first instant of time, and the collisions themselves are almost unimaginably crowded. When the beams cross, it is not two lonely particles meeting in the dark. It is dense bunches of them, countless particles sweeping through each other, producing collision after collision in the same tiny instant. Out of each meaningful collision sprays a fountain of debris, and the detectors must capture and sort it all, deciding in fractions of a second which events are ordinary and forgettable, and which might carry the rare signature worth keeping. The flood of data is so vast that not even the most powerful computers could store all of it. The machine must throw away the overwhelming majority of what it sees, almost instantly, keeping only the rare events that might hold an answer. It is a little like standing beneath a waterfall, asked to catch a few specific drops, and somehow doing it reliably for years. I want you to appreciate the human dimension of this as well, because it is easy to picture a machine and forget the people. The LHCb detector is tended by a collaboration of well over 1,000 scientists and engineers, drawn from dozens of countries, speaking dozens of languages, many of whom will spend the better part of their careers on questions that may not resolve within their lifetimes. There is a kind of quiet heroism in that, a willingness to give years of careful attention to a problem precisely because it is hard, precisely because the universe has not given up its answer easily. When the result finally comes, when a number is at last announced to the world, it carries inside it the patience of thousands of people and the slow accumulation of trillions of collisions. Nothing about it is hasty. Nothing about it is careless. That is why, when these scientists say they have found something, the world listens. And remember what they are listening for. Not a flash, not an explosion, not a dramatic signal that announces itself. They are listening for a tiny difference in counting, a few more decays of one kind than another, a faint asymmetry between how a particle and its mirror twin fall apart. The entire apparatus, the winter colder than space, the particles at nearly the speed of light, the fountains of debris, the oceans of discarded data, all of it exists to measure, with enough confidence to convince the most skeptical minds alive, whether matter and antimatter are truly identical mirrors, or whether, somewhere, the mirror is flawed. Everything we have built points at that one quiet question, and the patience finally paid off. In the next part, we are going to stand at the moment it finally happened. We are going to look at the result that came out of that patient machine beneath the border, the first time in history that scientists watched matter and antimatter behave differently in a baryon, in the very category of particle that ordinary matter is made from. It is the something that happened at CERN, and once you understand what it showed, you will also begin to understand why, even in their triumph, the scientists who found it had to admit that they still cannot fully explain what it means. Before we go there, hold one image of this machine in your mind as you rest, because it is a strangely comforting one. Right now, as you lie still, that great ring beneath the fields is most likely awake. Somewhere under the quiet border of two countries, in the engineered winter colder than space, particles are circling at nearly the speed of light, colliding, blooming into fleeting fragments of the early universe. While patient detectors watch and count, people are sitting in control rooms through the night, tending the question, keeping the long vigil. There is something soothing in knowing that even as you drift towards sleep, the search continues without you, carried forward by others in the dark, on your behalf, and on behalf of everyone who has ever wondered why there is something rather than nothing. You can let go of the question tonight, precisely because so many careful hands are still holding it. Rest for a moment in the cold and the quiet of that great ring beneath the fields. We are about to watch the mirror crack in the stuff of bodies and stars. So, here is what happened. In the spring of the year 2025, the scientists working with the LHCb detector announced a result that physicists had been chasing without success for decades. For the first time in the history of science, they had observed matter and antimatter behaving differently in a baryon. The mirror had finally been caught cracking in the very category of particle that you and the ground beneath you and the stars above you are actually made of. To understand why this landed the way it did, we have to slow down and look closely at exactly what they saw. The particle at the center of the measurement is a heavy and exotic cousin of the ordinary proton. Physicists call it the beauty baryon, or by its more technical name, the lambda b. Like the proton in your atoms, it is a baryon built from 3 quarks bound together, but one of those quarks is the beauty quark, the same heavy, unstable ingredient that made the meson studies so fruitful. This makes the beauty baryon a perfect hunting ground. It is a real baryon, kin to the matter you are made of, and yet it carries the beauty quark whose decays are known to expose the crack in the mirror. If matter and antimatter were going to part ways in a baryon anywhere, this was a promising place to look. The beauty baryon does not last. Like all these heavy particles, it is born in the violence of a collision, and then, almost instantly, it falls apart into lighter pieces. In this particular study, the physicists focused on a specific way it can decay, a channel in which the beauty baryon breaks into a handful of more familiar particles, a proton and several other lighter fragments flying outward together. And of course, alongside the beauty baryon, the collisions also produce its antimatter twin, the anti-beauty baryon, which falls apart into the mirror set of pieces, an antiproton and the antimatter versions of the rest. Now comes the heart of the method, and it is beautiful in its simplicity even though the execution is staggeringly hard. You count how many times the beauty baryon decays in this particular way. Then you count how many times its antimatter twin decays in the mirror way. If matter and antimatter are perfect reflections of each other, those two counts should be equal. The same particle, the same antiparticle, falling apart the same number of times into mirror image debris. Equal counts mean a perfect mirror. Any gap between the counts means the mirror is cracked. It means nature, at some level, prefers one over the other. The counts were not equal. When the physicists tallied the enormous pile of data, sifting the meaningful decays out of billions upon billions of collisions, they found that the beauty baryon and its antimatter twin did not decay in equal measure. There was a difference. The matter version and the antimatter version parted ways, falling apart at slightly different rates. The size of the difference came out to roughly 2.5%. Let that land. Not a difference buried impossibly deep, not a whisper at the very edge of detection, but a clear gap of a couple of percent between how matter and antimatter behaved. In the world of these measurements, that is a loud and unmistakable signal. But a number alone is not a discovery. This is one of the most important things to understand about how this kind of science works, and it is also, in its own way, deeply reassuring. Physicists do not get to announce a discovery the moment they see an interesting number, because numbers can lie. The universe is noisy. Random chance can pile up in ways that mimic a real effect. So before anyone is allowed to use the word discovery, the result has to clear a very high bar, a standard of statistical confidence that physicists treat almost as sacred. They ask a sharp question. If there were really no difference at all between matter and antimatter here, if the mirror were perfect, how likely is it that pure random chance could have produced a gap this large by accident? To answer that, they use a measure called sigma, a way of counting how far a result stands out from what random noise could plausibly produce. A result at 1 or 2 sigma is interesting but weak, easily a fluke. 3 sigma is intriguing, worth attention, but still not enough. The threshold the field demands before declaring a true discovery is 5 sigma. 5 sigma means the odds of the result being a random accident are smaller than roughly 1 in a few million. It is the line that separates a tantalizing hint from an established fact about the universe. The baryon result crossed that line. The measured difference reached a significance beyond 5 sigma. In the careful, conservative language of physics, that single fact transforms everything. It means this is not a fluke. It is not the detector playing tricks. It is not random noise arranging itself into a false pattern. It is a real property of the universe, established to the standard the field reserves for genuine discovery. For the first time, matter and antimatter had been caught behaving differently in a baryon, and the result was solid enough to stand. Now, I want you to feel why this particular crack in the mirror matters so much more, in a sense, than all the cracks that came before it, because of what a baryon is. Across all the earlier discoveries, the kaons in the 1960s, the B mesons around the turn of the century, the crack in the mirror had only ever been seen in mesons. And mesons, for all their importance, are not the stuff of the everyday world. They are fleeting, exotic, made of a quark and an antiquark, and they do not stick around to build anything. They are not in your hands. They are not in the chair, the floor, the bone, the blood. The ordinary matter of the universe, the matter that endured the great annihilation and gathered into everything that lasts, is made of baryons. Protons and neutrons are baryons. The nucleus of every atom in your body is a cluster of baryons. When we speak of the matter that survived, the 1 grain in a billion that became the cosmos, we are speaking of baryons. So for all those decades, there was a strange and frustrating gap in the story. We knew the universe was full of surviving baryonic matter. We knew the survival required matter and antimatter to be treated differently somewhere. And yet, in the baryons themselves, in the actual stuff that survived, we had never once directly caught that difference in the act. We had seen the mirror crack only in particles that are not what we are made of. It was a little like knowing a crime had been committed, finding the difference everywhere except at the scene that mattered most. This new result closed that gap. It caught the asymmetry, for the first time, in the very class of matter that builds bodies and stars. The crime, at last, was witnessed in the right kind of particle. There is a reason it took so long to catch the crack in a baryon, and understanding that reason makes the achievement land even more deeply. Baryons are simply harder to study in this way than mesons. Their decays tend to spread across many different possible outcomes, dividing the signal into smaller and smaller pieces, each one harder to measure cleanly. The asymmetries expected in them are subtle, and the backgrounds that can mimic or mask a real effect are stubborn. For years, physicists chased hints in the baryon family that flickered at the edge of significance and then faded, never quite reaching the threshold that would let them declare a discovery. It was a frustration that ran for the better part of a generation, the sense that the asymmetry surely had to be there in the very stuff of ordinary matter, and yet the universe would not quite let them prove it. The 2025 result is what finally broke that long stalemate. It is the accumulated reward of years of refusal turning, at last, into confirmation. Sit with the intimacy of that. You are made of baryons. Every atom of you is anchored by baryons. And for the first time, scientists have watched, directly, matter and antimatter of the baryon family refuse to be perfect mirrors of each other. The faint preference that may, in some ancient and amplified form, be the reason you exist at all, has now been seen in the same kind of particle you are built from. It is no longer an inference about distant cousins. It is a measurement in the family itself. The flaw that spared the universe has been observed, at last, in the matter that the universe is actually made of. And there is a poetry in the timing of it that is hard to ignore. We are the matter that survived the great annihilation, and after billions of years of gathering ourselves into stars and worlds, and at last into curious, thinking creatures, we have finally turned around and caught, in a laboratory of our own making, the very kind of preference that may be the reason we survived in the first place. The leftover matter built instruments delicate enough to detect the flaw that spared it. There is a circle closing in that, a sense of the universe coming to know, through us, the small asymmetry that allowed there to be an us at all. It is the kind of moment that, once you truly grasp it, is difficult to set down. This is the something that happened at CERN. Stated plainly, it is this: a machine beneath the border of two countries recreated, for countless brief instants, the conditions of the early universe. In that recreation it produced beauty baryons and their antimatter twins. Scientists counted, with overwhelming precision, how each fell apart, and they found that nature does not treat the two the same. Matter and antimatter in a baryon behaved differently by a couple of percent to a confidence beyond the strict 5 sigma standard of discovery. The mirror, in the stuff of ordinary matter, is cracked, and the universe, it turns out, has a measurable preference. Let me dwell on the difficulty of this measurement, because the more you understand what it took, the more astonishing the result becomes. Finding an asymmetry of a couple of percent sounds, on the surface, almost easy. A couple of percent is a difference you could notice in everyday life, a small change in a price, a slight tilt in a scale. But here that difference is buried inside an avalanche of complications. The beauty baryons are rare. They appear in only a tiny fraction of collisions, and they vanish almost the instant they are born. The debris they leave behind looks, at first glance, much like the debris of countless ordinary events that have nothing to do with the question. To find the signal the physicists must reconstruct the fleeting path of a particle they never directly see, working backward from the spray of lighter pieces, and they must do this millions of times to build up a count large enough to trust. And here is the subtlety that makes it truly hard. The machine itself is not perfectly even-handed. The detector might, through some quirk of its design, catch matter slightly more easily than antimatter, or measure one a touch more often than the other. If the physicists were careless, such an instrumental bias could masquerade as a real asymmetry, a false crack in the mirror that lives in the machine rather than in nature. So an enormous part of the work is making absolutely sure that the difference they measure is the universe speaking and not the apparatus deceiving them. They cross-check against other particles whose behavior is already understood. They flip and test and control for every effect they can imagine. Only when every alternative explanation has been ruled out do they allow themselves to say that the asymmetry is real. The 2.5% that survived all of that scrutiny is therefore not a casual figure. It is a number that fought its way through years of doubt. I also want to make the meaning of 5 sigma vivid, because it is the hinge on which the whole claim turns, and it deserves to be felt rather than merely stated. Imagine flipping a coin again and again, and suppose the coin is perfectly fair, with no real bias at all. Every so often, by pure luck, you will get a run of heads that looks suspicious, a streak that might tempt you to believe the coin is loaded. A weak result, 2 or 3 sigma, is like a short streak. Striking, but the kind of thing chance produces all the time. 5 sigma is a streak so long, so extreme, that to attribute it to luck you would have to believe you had witnessed something that random chance would produce less than once in millions of honest attempts. At that point, clinging to coincidence becomes the unreasonable position. The asymmetry in the beauty baryon cleared that bar. The universe was not flipping a fair coin. The coin of matter and antimatter is, in this particle, genuinely weighted. There is one more thing worth holding before we turn toward the trouble, and it is the sheer lineage of this result. Think of the long chain of discovery that led here. The first faint crack in the mirror found in the kaons in the 1960s. The confirmations in the mesons around the turn of the century. Decades of ever finer measurements, each one extending the reach of the question a little further. And now, at last, the crack found in a baryon, in the family of particle that ordinary matter belongs to. It is the completion of a search that spanned more than half a century and the working lives of generations of physicists. To stand at the moment when the mirror is finally caught cracking in the very stuff of bodies and stars is to stand at the end of one of the longest and most patient hunts in the history of science. And it is also, as we are about to see, to stand at the beginning of a deeper bewilderment. It would be easy to end the story here on a clean note of triumph, and many tellings of it do. A great machine, a great discovery, a long-sought asymmetry finally caught in the right kind of particle. It is a genuine landmark, the kind of result that earns its place in the history of physics. But if we stopped here, we would be telling you only the half that is comfortable, and we promised at the very beginning that we would be honest about the part that is not. Because the most remarkable thing about this discovery is not the relief of finally finding the crack in the mirror. The most remarkable thing is what happens when you ask the obvious follow-up question, is this enough? Is this, at last, the explanation for why the universe survived? Is this the thumb on the scale we have been hunting for 100 years? And the answer that the scientists themselves give, the answer that turns a story of triumph into a story of genuine mystery, is no, not even close. That is the strange and beautiful core of what happened at CERN. They found exactly the kind of thing they had been looking for. They confirmed that matter and antimatter differ in the baryon family. They did it to the highest standard their field allows. And it still does not explain you. It still does not account for the 1 grain in a billion that became everything. The crack is real, and the crack is in the right place at last, and it is still somehow far too small to have done the job. The discovery does not close the mystery, it sharpens it. It takes the vague unease of 100 years and presses it into a single, precise, unanswerable point. In the next part, we are going to face that point directly. We are going to understand why a real, confirmed 5 sigma discovery of matter-antimatter asymmetry in the very stuff of ordinary matter still leaves the deepest question completely open. We are going to look at the gap between what we found and what the universe demands, and we are going to see just how vast that gap truly is. This is where the word unexplained earns its place, not as a sales pitch, but as the plain and humbling truth. Let this paradox settle over you before you sleep, because it is one of the most beautiful shapes a piece of knowledge can take. We search for something for 50 years. We finally found it in the right place, to the highest standard our science allows. And finding it did not give us the answer. It gave us a clearer view of the size of the question. Most discoveries make the world feel a little more explained, a little more closed. This one did the opposite. It confirmed exactly what we hoped to confirm, and in doing so it showed us, more precisely than ever before, how much we still do not understand. There is a rare and honest kind of progress in that, the progress of learning the true dimensions of your own ignorance. The universe answered the question we asked, and the answer was, in effect, that we have been asking too small a question all along. Stay with me in the quiet a little longer. The most honest part of the story is the part still to come. Here is the question that turns a triumph into a mystery. We found the crack in the mirror, at last, in the right kind of particle. So, is it enough to explain why the universe survived? And the honest answer, the one the scientists give, without flinching, is that it is not. To understand why, we have to do something that physics rarely lets us do so cleanly. We have to compare 2 numbers. One is the amount of matter-antimatter difference that our best theory of reality can supply. The other is the amount the universe actually needed in order to leave behind everything you see. And the distance between those 2 numbers is one of the largest, most stubborn gaps in all of science. Let us name the theory plainly. Physicists call it the Standard Model. It is the crowning achievement of a century of particle physics, a single framework that describes all the known particles and nearly all the forces that act between them. It is not a vague sketch. It is the most precisely tested theory humanity has ever produced. Some of its predictions have been confirmed to a dozen decimal places, an accuracy comparable to measuring the distance across a continent and being correct to the width of a human hair. When we recreate the early universe in the collider and watch particles decay, the Standard Model tells us, with breathtaking reliability, what we should see. It is, by almost any measure, the most successful description of reality we have. And the Standard Model does contain CP violation. It does allow matter and antimatter to be treated slightly differently. The crack in the mirror is written into its equations, woven into the way the quarks mix and transform. In fact, the baryon discovery we just walked through is, so far, consistent with what the Standard Model predicts. The theory anticipated that a difference of roughly this size could appear in these particles, and the measurement landed in the neighborhood the theory pointed to. In that narrow sense, the discovery is a victory for the Standard Model. It found exactly the kind of asymmetry the theory said should be there. But now we ask the cosmic question. Take all the CP violation the Standard Model allows, every crack in the mirror it can produce, across every particle, and add it up. Pour all of it into the early universe. Let it do its work in the furnace, tipping the ledger, sparing a little matter from the great annihilation. How much matter would survive? How large a remainder would the Standard Model's asymmetry leave behind? And the answer is devastating. It would leave a universe almost perfectly empty. The amount of surviving matter the Standard Model can account for falls short of the amount we actually observe by something like 1 billion-fold, by many, many orders of magnitude. The theory's thumb on the scale is real, but it is laughably, catastrophically too light. Let me put that gap in terms you can feel. Imagine you needed to fill a great reservoir, a lake, to keep a city alive. The universe is that full reservoir, and the Standard Model, asked to fill it, arrives with something closer to a single cup of water, not half the lake, not a tenth of it, a cup against a lake. The crack in the mirror that we have spent a century discovering, confirming, and celebrating, including this newest and most intimate confirmation in the baryons, is real in every case. And in every case, it is wildly insufficient to explain the world it was supposed to explain. The universe is overwhelmingly full of matter. Our best theory, working as hard as it possibly can only spare the faintest trace. This is why the scientists, even in the glow of a genuine discovery, are so careful to say that they cannot fully explain what they have found. It is not false modesty, it is precision. The baryon result is a real and important measurement of CP violation, but it does not solve the asymmetry of the universe. If anything, by confirming once again that the asymmetry behaves roughly as the Standard Model expects, it deepens the puzzle, because it tells us that the answer we need is almost certainly not hiding in the places we already know how to look. The known sources of the crack are accounted for, and they are not enough. Something else, something we have not yet found, must be doing most of the work, and we do not know what it is. So what could it be? This is where physics becomes humble, and where the honest answer to almost every question becomes the same 3 words: we do not know. But not knowing is not the same as having no ideas, and the ideas that physicists have proposed are some of the most fascinating in all of science. Let me walk you through the leading possibilities, gently, the way you might consider doors in a long, dark hallway, none of them yet opened, each one promising in its own way. The first possibility is that there are particles we have not yet discovered. The Standard Model describes the particles we know, but there is no law that says it describes all the particles that exist. There may be heavier, hidden members of the particle family, too massive to be made even in our greatest machines so far, that carried far more CP violation in the early universe than anything we can currently produce. If such particles existed in the first fraction of a second, when the furnace was hot enough to make them, they could have tipped the ledger far more strongly than the particles we know how to study today. The crack in the mirror we measure now would then be only the small, surviving echo of a much larger crack that operated long ago in particles that have since vanished from the cooling cosmos. Finding such particles, or ruling them out, is one of the great quests driving physics forward. The second possibility moves the spotlight to a quiet and ghostly family of particles called neutrinos. Neutrinos are almost nothing. They have a tiny whisper of mass. They carry no electric charge, and they pass through ordinary matter so easily that trillions of them are streaming through your body right now, in this room, without touching a single atom of you. For a long time they were thought to be utterly massless and utterly simple, but we have since learned that they have mass after all, and that they shift and transform as they travel, and these discoveries opened a door. Many physicists suspect that neutrinos, or their heavier unseen relatives, may hold the key to the whole mystery. There is an elegant idea, given the name leptogenesis, in which the asymmetry of the universe began not with the matter we are made of, but with these ghostly particles in the early cosmos, an imbalance among the neutrinos that was later converted, through subtle processes in the furnace, into the surplus of ordinary matter that became you. It is a beautiful idea. It is also so far unproven. We are only beginning to build the experiments that could test it. The third possibility is stranger still, and it touches the very framework of the laws. Perhaps the missing asymmetry came from processes that operated only in the extreme conditions of the early universe, processes that are effectively frozen and silent today. In the searing heat of the first instant, the forces of nature behaved differently than they do now, and there may have been windows of opportunity, brief phases as the universe cooled and changed state, during which matter could be created out of balance in ways that are simply not available in the cold, settled cosmos we inhabit. If so, the answer is not a particle we can catch, but a moment we can never revisit, a fleeting condition of the early universe that did its work and then closed forever. We can only try to reconstruct it through theory and through the faint fossils it might have left behind. There is a fourth thing worth naming, not a separate door so much as a condition that the true answer must satisfy, because it sharpens what we are really searching for. Long ago, a thoughtful physicist laid out the basic requirements that any explanation of the surviving matter would have to meet. The universe needed a way to treat matter and antimatter differently, which is the crack in the mirror we have been discussing. It needed a way to actually change the balance between them, to convert one into the other, or to create one without the other. And it needed all of this to happen during a time when the universe was out of its calm equilibrium, in the turbulent rush of the early cosmos as it expanded and cooled. Each of these conditions is necessary, and the known physics satisfies all of them in principle, yet supplies the first one in a quantity far too small. So the search is not aimless. We know the shape of the answer we are missing. We know it must involve a larger source of the crack in the mirror than anything we have yet measured. We simply have not found where that larger source hides. The frame of the question is clear. The answer inside the frame is blank. Notice what all of these ideas have in common. Every one of them reaches beyond the standard model. Every one of them says, in its own way, that our most successful theory of reality, the one tested to a dozen decimal places, is incomplete. That there is physics we have not yet discovered, hiding either in particles too heavy to make, or in neutrinos too ghostly to catch, or in moments too ancient to revisit. The matter-antimatter asymmetry is not just an unsolved problem. It is one of our clearest signposts pointing past the edge of everything we know, telling us that the map is not yet finished, that there is more territory beyond the part we have charted. And this is why discovery like the one at CERN matters so much, even though it does not solve the mystery. Because the only way to find the missing physics is to measure the known physics with ever greater precision, and to watch for the moment when the universe departs even slightly from what the standard model predicts. The baryon result is consistent with the theory for now, but the measurements will grow sharper. More data will pour in, and somewhere in that growing precision, physicists are watching for a crack within the crack, a place where matter and antimatter differ by just a little more, or a little less, or in just a slightly different way than the standard model allows. That tiny deviation, if it ever appears, would be the thread that unravels the whole mystery, the first direct glimpse of the new physics that made you possible. So when you hear that scientists found something at CERN and still cannot explain it, understand that this is not a failure. It is the most honest possible description of where we stand. We have measured the flaw that made the universe. We have weighed it in the oldest light in the sky and now caught it in the very stuff of bodies and stars. And we have confirmed, again and again, that the flaw as we understand it is far too small to have done what it did. The universe exists by a margin our theories cannot yet account for. You exist by a margin our theories cannot yet account for. The surplus of matter that became your body is, at this moment in human history, a genuine and unsolved mystery, one of the deepest we have. I want to return for a moment to that comparison of the two numbers, because it is so stark that it is worth saying in more than one way. The asymmetry the known laws can produce, set against the asymmetry the universe actually required, is not a near miss. It is not a matter of the theory being a little low, the kind of gap a small correction might close. The shortfall runs to many orders of magnitude, a difference so large that no reasonable adjustment of the known physics can bridge it. When a theory is wrong by a factor of 2, you suspect an error in your calculation. When it is wrong by a factor of 1,000,000,000, you are forced to suspect that something fundamental is missing from the theory itself, an entire piece of nature that has not yet shown its face. That is the situation we are in. The matter-antimatter asymmetry is not a small discrepancy to be tidied up. It is a hole in our understanding the size of a universe. And I want to be careful and fair here, because it would be easy to overstate this into despair, and that is not the truth either. The standard model is not wrong in the way that a discredited idea is wrong. It is spectacularly right about almost everything it describes. The honest situation is subtler and more interesting. We have a theory that works beautifully within its domain, that predicts the outcomes of experiments to staggering precision, and that we nonetheless know with certainty to be incomplete, because the universe contains things it cannot explain. The surviving matter is one of those things. So is the nature of the dark matter that seems to outweigh ordinary matter many times over. So is the strange acceleration of the cosmos. These are not signs that physics has failed. They are signs that physics is standing at a frontier, with a reliable map of the settled country behind it and a vast unmapped wilderness ahead. Let me also be honest about the role of this particular discovery within that larger picture, because it is easy to misunderstand what was actually found. The baryon result is, so far, broadly consistent with what the standard model predicts. That is worth saying plainly. It did not, by itself, reveal the missing physics. It did not catch the universe doing something the theory forbids. What it did was extend our reach, opening a new family of particles to precise study, a family directly tied to the matter we are made of. And in science, opening a new place to look is often how the decisive clue is eventually found. The first measurement establishes the territory. The measurements that follow, sharper and sharper, are where a deviation, if one exists, would finally show itself. This discovery is the doorway, not the room beyond it. But you cannot enter a room whose door you have not yet found. So picture the physicists now, in the wake of this result, doing what good scientists always do with a confirmed discovery. They are not resting, they are sharpening. They are gathering more data, refining their methods, planning measurements of related particles, all with one quiet hope held in common, that somewhere, in some decay, in some careful count of matter against antimatter, the universe will at last say something the standard model did not predict. A difference a little larger than expected, or a little smaller, or pointing in a direction the theory does not allow. That single deviation, whenever it comes, would be the loose thread, the first direct sighting of the new physics that tipped the ledger in the first instant of time. They do not know if it will come in 5 years or 50, or in the work of scientists not yet born. But they keep looking, because the alternative, to stop asking why we are here, is unthinkable to a curious mind. There is something I find quietly moving in that, and I hope you feel it too as the room grows dark around you. We have built the largest machine in history, gathered thousands of the most capable minds alive, and recreated the first instant of time 10,000 times a second beneath a quiet field in Europe. And at the end of all that effort, standing before the question of why there is something rather than nothing, why there is a you rather than an empty glow, the most truthful thing the finest scientists in the world can say is that they do not yet know. The mystery is not shrinking away from us. It is standing right where it has always stood, vast and patient, waiting. In the final part, we are going to step back from the machines and the measurements and let the meaning of all this settle over you. We are going to return from the early universe to this room, to this night, to the slow rhythm of your own breath. And we are going to ask what it means to be the surviving remainder of an imbalance that science can measure but cannot yet explain. Stay with me for the close. And let go, as you rest, of any worry that the mystery being unsolved makes it somehow less true or less yours. The opposite is the case. Every breath you take is solid, undeniable proof that the imbalance happened, whether or not we can yet explain it. You do not need the explanation in hand to trust the fact. The matter that survived is here, gathered into a body, warm and breathing in the dark, and that survival is the most concrete thing in the room. The why of it can remain open for 1,000 more years and not change, by a single atom, the reality of you lying here tonight. The question is unfinished. You are not. You are complete and present and real, a finished sentence written in the language of surviving matter, even as the cosmos goes on puzzling over how it came to write you at all. We are going home now, from the edge of the cosmos back to the quiet of your own body, carrying the mystery gently with us. Come back now, slowly, from the cold ring beneath the fields and the furnace of the first second, all the way home to this room, to the weight of your body against the bed, to the quiet, to the dark gathering softly in the corners. We have traveled to the edge of what humans know and found a mystery waiting there, unsolved, vast, and patient. And now I want to bring that mystery the rest of the way home, because it does not actually live in a machine in Europe or in the first instant of time. It lives in you. It has been living in you all along. Think about what we have learned, and then look at yourself in its light. You were raised to believe, without ever being told, that you are an ordinary object in a sensible universe, a body among bodies, a thing that exists because things exist. But that is not what the science says. The science says you are the surviving remainder of an almost perfect cancellation. You are what was left when nearly everything else turned to light. For every particle in your body, there were once a billion others, matter and antimatter together, that met and annihilated and vanished into the glow that still fills the sky. You are not the rule. You are the exception that the rule could not quite erase. You are the one grain in a billion, gathered across 10 billion years, wearing a human face in a dark room. Let that change, just slightly, the way the weight of your own body feels tonight, the slow rise and fall of your chest as you breathe. That is matter that should not be here. The warmth moving through your hands, the faint pulse you can feel if you go looking for it, the quiet machinery of a living body at rest. All of it is salvage from a catastrophe so complete that survival itself was a rounding error. The iron in your blood that makes it red was forged in stars that died long before the sun was born, and those stars were built from the lonely remainder that escaped the great annihilation. You are wearing the leftovers of creation as a body. You are the imbalance, made warm, made aware, lying still and listening. And here is the part I find almost unbearably beautiful. The flaw that spared you is one that science can measure, but cannot yet explain. We have built the greatest instruments in human history, and we have caught the crack in the mirror at last, in the very stuff you are made of. And still, standing before the question of why you are here rather than nothing, the most honest scientists in the world say that they do not fully know, which means that you are not only the survivor of an ancient imbalance, you are the survivor of an imbalance that remains, to this day, a genuine mystery. You are an unanswered question, breathing in the dark. There is a temptation to feel small in the face of all this, to feel like a speck against the enormity of the cosmos and the depth of what we do not understand. But I want to offer you the opposite feeling tonight, because I think it is the truer one. You are not a speck that the universe happened to ignore. You are the precise and improbable thing the universe failed to destroy. The empty cosmos was the easy outcome, the expected one, the one the rules wanted. You are the difficult one. You are the result that required a flaw in the fabric of reality, a thumb on the scale that we cannot yet locate, a margin so thin it defies our deepest theories. The universe did not make you carelessly. It made you against the odds it set for itself. Whatever else is true, your existence is not cheap. It cost the cosmos almost everything it had. And the question that remains, the unsolved one, the why behind the surplus of matter, is not a gap you need to fear. I want you to feel that clearly as you drift towards sleep. An unanswered question is not a darkness pressing in. It is a vastness opening out. It is the cosmos admitting that it is larger than our maps, that there is more to find, that the story of where you came from is not finished and may not be finished for generations. You get to exist inside an open question. You get to be a chapter in a mystery that the smartest people alive are still trying to read. There is room in that to rest. There is room to wonder without needing to conclude. Think for a moment about the journey those particles took to become you, because it is the longest journey there is, and you are its destination. They survived the great annihilation in the first fraction of a second, when nearly everything else turned to light. They drifted through the expanding dark for hundreds of thousands of years, too hot and too scattered to gather. Slowly, as the universe cooled, they formed the first simple atoms, the lightest elements, vast quiet clouds of them spreading through a cosmos with no stars yet to light it. And then gravity, patient beyond all patience, began to pull those clouds together, knot by knot, until the first stars ignited and the long darkness ended. Inside those stars, under crushing pressure and heat, the simple atoms were forged into heavier ones, the carbon and oxygen and iron that bodies require. And when those stars died, some gently and some in catastrophic blasts, they scattered their forged elements back into space, seeding the clouds from which new stars and new worlds would form. Your atoms rode that cycle, perhaps many times over, before they ever found their way into the earth, into the food you have eaten, into the slow construction of the body that is lying here now. Every one of them is older than the Sunday. Every one of them is a survivor of the beginning of time. And now those ancient survivors are arranged, briefly, into the shape of a person who can know all of this. That is the part that should stop you, if anything can, on the threshold of sleep. The leftover matter of the cosmos has, after 10 billion years of burning and drifting and gathering, folded itself into a form that can look back at its own origin and feel something about it. You are the universe's way of noticing that it survived. You are the remainder. Become aware of being the remainder. When you wonder where you came from, it is the surviving matter of the first instant wondering about itself, through the only kind of structure complex enough to ask. There is no need to reach for anything grander than that, because nothing is grander than that. The cosmos kept one grain in a billion, and that grain learned to ask why it was kept. I do not want to pretend to you that the asking has an answer yet, because it does not, and the whole spirit of this night has been honesty. We do not know what tipped the ledger. The greatest scientists alive have measured the imbalance with exquisite care and have confirmed again and again that they cannot yet explain it. But I want to offer you a gentler way to hold that uncertainty than the way we are usually taught to hold it. We are trained to treat an unanswered question as a kind of debt, a thing that nags and presses until it is paid off and closed. But there is another way to hold a question. You can hold it the way you hold the night sky, not as a problem demanding solution, but as a presence inviting wonder. The question of why you exist is not a debt hanging over you. It is a door standing open onto something larger than anyone has yet mapped. And you are allowed to stand in that doorway and simply breathe, without needing to walk through it tonight. Consider, too, what it means that this mystery lives inside you rather than far away. We began this night with a machine beneath a field in Europe, with collisions and detectors and numbers, all of it distant and cold and precise. But the asymmetry the machine studies is not really out there in the machine. The machine only recreates in miniature the thing that already happened in you, to the matter you are made of, in the first instant of time. You did not have to travel to CERN to encounter the great unsolved question of existence. You only had to lie still and remember what you are. The mystery is not in Geneva. It is in the weight of your own hand resting on the blanket. It is in the warmth that will not leave your body until you do. It has been with you your whole life, closer than your own breath, and tonight you simply turned and looked at it. So let the looking soften into rest. You do not have to keep holding the thoughts tightly. Let them loosen, the way the muscles of your shoulders can loosen, the way the day loosens its grip as the light goes. The science will still be here in the morning. The scientists will go on with their patient work, gathering their data, sharpening their measurements, watching for the deviation that has not yet come. None of it requires your attention tonight. The universe carried its surviving matter for 10 billion years without your help, and it will carry the matter that is you through this night just as faithfully, whether you are awake to supervise it or not. You are allowed to set it down. You are allowed to trust the same patient process that made you to hold you while you sleep. So let the room go dark. Let the science settle into the background, the way the oldest light in the sky has settled into a faint and constant warmth you will never feel but which surrounds you all the same. The darkness of this room is a small piece of the great darkness between the stars, the same dark that the surviving matter drifted through as it gathered itself slowly into worlds. The quiet of this hour is a small piece of the silence that followed the great annihilation, after the fire, after the light, when the lonely remainder was all that was left, and the long patient work of becoming everything had only just begun. You are lying inside that story. You always have been. Tonight you simply know it. There is a quiet symmetry, a gentle one this time, in ending a story about cosmic imbalance with the act of falling asleep. All day your body leans forward into the world, spending energy, asserting itself, holding its shape against the constant pull toward dissolution. Sleep is the nightly loosening of that effort, the moment the surviving matter that is you stops striving and simply rests in what it is. And in that loosening there is an echo of the deepest fact about you, that your existence was never something you earned or maintained by force, but something you were given, freely and improbably, by a flaw in the early universe that no one yet understands. You do not have to hold yourself together tonight. The same imbalance that has carried your atoms across 10 billion years is still carrying them now, and it asks nothing of you in return, except that you let it. Let your attention drift, if it wants to, away from the particles and the machines and the unanswered questions, back toward the simple sensations of the body at rest, the weight of your head, the slow tide of your breath, the faint sounds of the room settling around you. Each of these ordinary things is made of the extraordinary remainder we have spent this night describing, but you do not need to think about that anymore. You can simply feel it. The wonder does not require your effort to be true. It is true while you sleep, true while you forget it, true in the morning when you wake and remember none of this. The matter that survived the beginning of time does not stop being miraculous when you stop paying attention to it. It just goes quietly on, being you. Breathe in slowly. That breath is built from atoms that survived the beginning of time. Breathe out. You are returning a little of yourself to the air, as you always do, as everything does, the leftovers endlessly rearranging themselves into new shapes, into bodies and breaths and quiet rooms. There is no need to hold on tightly to any of it. You are part of a flow that began before there were stars and will continue long after this night is forgotten. The imbalance that made you will go on making others, grain by grain, world by world, for as long as the cosmos endures. Notice, if you can, how the enormity of all this has begun to feel less like a weight and more like a kind of spaciousness. That is the gift hidden inside a question this large. A small worry crowds the mind and presses in. A vast wonder does the opposite. It opens the room outward until the ceiling seems to dissolve into the dark between the stars, until the walls no longer feel like boundaries, but like the thinnest of veils between you and a cosmos still busy making and unmaking itself. You are not shut inside a small life tonight. You are resting inside something immense and unfinished and quietly generous, something that found a way to keep you when, by every rule, it should have kept nothing. There is room to breathe in that. There is room, more than enough, to sleep. If your eyes have grown heavy, let them close. You do not need to follow the science any further tonight. You do not need to solve the mystery. The scientists have not solved it either, and they have given their lives to it. And there is a strange comfort in that, in being uncertain together, in resting inside the same vast, open question as the people who understand it best. The not knowing is shared. The wonder is shared. And the matter that you are made of, the surviving remainder of the first instant of everything, is finally, after 10 billion years of gathering and burning and drifting, allowed to do the simplest and most human thing of all. It is allowed to rest. If your mind wanders back, in these last waking moments, to the image of the great machine beneath the fields, let it be a peaceful image now, rather than a restless one. Picture the long ring in its engineered winter, the patient detectors, the people keeping watch through the night. They are not anxious about the unsolved question. They have made their peace with it long ago, the way you make peace with a mountain you intend to climb for the rest of your life. The not knowing is not a wound to them. It is the reason to get up in the morning, the open horizon that gives the work its meaning. And tonight, that same horizon can give your rest its meaning too. You are not lying in the dark beneath a closed and finished sky. You are lying beneath an open one, a cosmos still unfolding its secrets, with room left in it for wonder that has not yet been spent. There is a final tenderness I want to leave you with, the kind that is easier to feel at the edge of sleep than at any other hour. For all the vastness we have traveled through tonight, the billions of particles, the orders of magnitude, the 10 billion years, the thing it all comes down to is small enough to hold in two hands. It comes down to you, here, now, breathing. The whole immense story of matter and antimatter, of annihilation and survival, of machines and measurements and unanswered questions, has as its quiet conclusion a single living body at rest in a darkened room. That is not a small ending for a cosmic story. It is the only ending that matters. The universe spent almost everything it had, and what it kept, against all the odds it set for itself, was the capacity for a moment exactly like this one, soft, warm, aware, ready for sleep. So rest. Let the one grain in a billion lie still in the dark. Let the imbalance that built the universe close its eyes for a while. Whatever happened at CERN, whatever the next discovery reveals, whatever the answer to the great question turns out to be, none of it asks anything of you tonight except this: to breathe, to be here, improbably, warmly, against all the odds the cosmos set, to be the leftover light of creation, dreaming. Let the breath slow on its own. There is nothing left to do now, nothing left to understand, no question that needs answering before you close your eyes. The cosmos kept you without asking your permission, and it will keep you through this night the same way, gently, automatically, the way it has kept every grain of surviving matter since the first instant of time. You are held by the oldest process there is. You can stop holding yourself. Feel the bed take your weight. Feel the dark settle like a soft tide over the room. Somewhere far away, the great machine hums on in its winter, and the patient people keep their watch, and the question stays beautifully open, and none of it needs you tonight. Sleep now. You were always made of survivors. You can let them carry you the rest of the way.